In this video, we're going to talk about doing now calculus with parametric curves. So, let's suppose that we've got a set of parametric equations, x equals f of t and y equals g of t. And let's just suppose, for the time being, for argument's sake, that we can actually write y explicitly as a function of x. So, some h of x. Well, then certainly, if x is f of t, we can take g of t, which is our y, and that equals our h equals f of t, just putting the f of t in for x. All right. So when we think doing calculus with something, we'll probably want to take its derivative, right? One of the first things that you're interested in calculus, when you come up with a new thing, you want to know how is that thing changing? What's its derivative? So let's do that here. Let's differentiate both sides with respect to t. Use a chain rule on the right-hand side, so that's where this is coming from. Now let's solve for our h prime of f of t. So that's literally just taking the g prime of t and dividing by f prime of t. Remember now that f of t is just x, though, right? So h prime of x, so this is the derivative with respect to x, is the quotient of these two derivatives with respect to t. So if we write this in Leibniz notation, remember y was h of x, so the left-hand side here would be dy dx. The derivative of y with respect to x, so how y is changing with respect to how x is changing, is equal to the quotient of how y is changing with respect to t over how x is changing with respect to t. All right, so this is how we're going to calculate the derivative of y with respect to x. And so if we want to do things like slopes of tangent lines, this is how we would do a slope of a tangent line to a parametric curve. All right, so let's do one of those. Let's find an equation of the tangent line to the curve defined by those parametric equations at the point that's given there, the 2, e. All right, so as soon as we see the word tangent, we should immediately think derivative, because we need slope of that tangent line. So the first thing we're going to do, find the derivative. So derivative is dy dt over dx dt. You need to use a chain rule on the e to the t squared. That gives us 2t e to the t squared. Here, this is for the dx dt, this is t to the 1/2, so its derivative would be 1/2 t to the negative 1/2. We could simplify that if we wanted to, but really we just want the slope of the tangent line. Now notice, even though this says derivative of y with respect to x, it's in terms of t. So if I want to find the slope, remember slope is a number. Slope is not an expression with a variable in it. Slope is a number. I've got to plug something in for the variable to actually find the slope. In this case, I've got to plug in something for t. Notice I'm not giving anything here that is a t value, right? I'm giving an x value and a y value. However, I can figure out the t value from the point. Notice that if you plug in 1 for t into both x and y, you get the point 2, e. So when t is 1, we get x is 2 and y is e. So 1 is what we're going to want to plug into the derivative. So in this case, you'll get 4e when you're done. They give us the point already. We now have the slope, so we can just use our point-slope form to find the equation of the tangent line. So we get y minus e equals 4e times x minus 2. What are some other so here's a graph of this situation here. Sorry. So here is the parametric curve, and here is the line tangent at the point 2, e. All right, what's another thing that we are asked for using calculus and derivatives? One of those other things is concavity. So this problem asks what values of t is the parametric curve concave upward? Well, remember that concavity is determined by the second derivative. To get to the second derivative, we need to take the first derivative. So dy dx again is dy dt, which is just e to the t over dx dt, which is 2t. Now, you're probably very, very, very tempted to just now to say the second derivative is the second derivative of y with respect to t over the second derivative of x with respect to t. That is not correct. Okay? We want the second derivative of y with respect to x, right? Not the second derivative of y with respect to t and the second derivative of x with respect to t. All right, so what we really have to consider now is we have a new set of parametric equations. The x still changes like the x does. The x is t squared plus 1. The new quote-unquote y part of the parametric equation now is dy dx. It's the derivative piece, which is the e to the t over 2t. So when we want to do the second derivative, we take the derivative of the first derivative, so dy or d dt of dy dx, so the derivative of dy dx with respect to t over derivative of x with respect to t. So this is how we get the second derivative, not dy, the second derivative of y with respect to t and the second derivative of x with respect to t. The second derivative of x with respect to t isn't telling you how x is changing. It tells you something about the concavity of x with respect to t. That's not going to help you to find the concavity with respect to x. Okay? So you have to do it in this fashion. All right. On top here we have a quotient rule. You can check if that's correct. And then it's still over dx dt, that same 2t. Simplify, you get this. E to the t is always positive, so the only things that could be positive or negative here are the t minus 1 and the t cubed. It's not too hard to see that the second derivative is positive when t is less than 0, because both of those then will be negative, so you'll get a positive. And when t is greater than 1, because again, both of those will be positive, so you'll get a positive. So therefore, for the t values that the curve is concave up on, will be from negative infinity to 0 and 1 to infinity here. And here's what that graph looks like. You can see here, this part's not hard to see that you've got concave up here. Notice you've actually got a vertical tangent here. You can check that this is what you get when you put in 0 for t. The scale is by 2's here, so that's the 0.10. So here it's concave up, and then here you can see again we get this kind of switch in concavity. Here it's concave down, but here it's concave up. All right, another calculus thing that we do is areas. So let's do the area between those two curves. Or excuse me, not between those two curves. The parametric curve defined by those two equations and the x-axis. So I think probably one of the best first things you want to do is get a graph. You can do that on your calculator. It's probably a little bit easier to do this on your calculator than on by hand. So here's what the graph of the function looks like. So the area that we're interested in is this part here. So we probably need to know where this hits the x-axis. Well, this will hit the x-axis, or the curve hits the x-axis, of course, when y is equal to 0. So the first thing we're going to do is set y equal to 0 and find the t values. That's not hard to do. We can get t as 0 or 3. All right, so now what about the area? Well, remember the area is the integral of the function with respect to x. Well, usually we refer to the function as y, so we would have the integral of y with respect to x, so the integral of y dx. Now this negative sign here in front is coming from the fact that the curve here has gone below the x-axis. So that's why we've got a negative out in front. But in general, we're doing the integral of the function, or integral of y, because that would be the height of your rectangle, with respect to x, because that would give you your width of your rectangles. All right. So y is the t squared minus 3t. So that's just a direct substitution. The dx, of course, then is the derivative. Okay, it's the differential with respect to x. We'll put that now with respect to t, just take the derivative. And now we have something that we can integrate. Take an antiderivative and plug in the endpoints, and if you want to simplify, you get that 6 root 3 over 5 as your final answer. Again, we had to, there's a little bit of trickiness, if you will, that you have to worry about when doing some of the things with calculus with parametric equations and in polar coordinates coming up. You have to make sure that, well, in this case, when we did the area, I needed to make sure I have positive area. Well, this area here is trapped under the x-axis, so I had to put the negative in front to make it positive. Another thing that pops up is if you've got a set of parametric equations that just draws the graph out over and over and over and over again, you want to make sure that the graph is only drawn one time for your bounds for your integral. All right, one more here. Let's find the length of the curve. To find the length of the curve in this case, we want to go back and remember how we did length of curve back in Chapter 8. Remember that we needed to integrate the differential of the arc length, and back then we also said that we had that nice Pythagorean relationship between differential of arc length and the differentials of x and y. So now we're going to quote-unquote divide everything by dt squared to give us this relationship, and now solve for ds. We'll multiply, or take the square root of both sides and then multiply by dt. So here's the square root of both sides and then multiply by dt. Multiply, quote-unquote multiply. Just changing the derivative notation into its equivalent differential notation. So now we've got the differential with respect to arc length in terms of the differential with respect to time. So now we can do the arc length. So this one, I've got my bounds goofy here. This should be 0 less than or equal to t less than or equal to 3. The 0 should be here. The t should be here. So integrate from 0 to 3 because those are the bounds of the differential of arc length. So the derivative of x with respect to t is e to the t minus e to the minus t, quantity squared. Derivative of y with respect to t is -2. We'll square that. Bounds are 0 to 3 because, again, this t should be in the middle here, not on the left-hand side. All right. Now, in these arc length problems, just like what we saw before in Chapter 8, if you're able to do the problem, there must be some way it's been rigged so that you can actually simplify this and take this antiderivative. If you multiply this out, this first term out here, if you FOIL it out, you'll get a -2 in the middle. This is a +4. So when you combine those two things together, you get a +2 in the middle. So again, remember, when you FOIL this out, you got a -2 in the middle. All we've done is change that minus to a plus, so this refactors as almost the exact same thing. The only thing that's different is now a plus sign in the middle instead of a minus. Square root of the square just gives me what's on the inside there. Don't need to worry about absolute values here because the inside can never be negative. Take an antiderivative. Plug in the endpoints. So you get e cubed minus e to the minus cubed. E to the minus 3. Again, notice that if you're doing one of these arc length problems and you're actually able to calculate the arc length, then it's rigged in the sense that you can actually do some sort of an algebraic trick here to be able to simplify that radical.